Hi, everybody. I've been kind of in the background for a while at the NavHub talks, but today I thought I'd give it a go at hosting. And Lee's going to be in the background helping with the technical stuff, technical side of things. So today we have Jennifer McHenry here from Florida State University, and she's going to be talking about her project on how projecting marine species range shifts using just temperature information can be a bit misleading. And I'm really interested to hear about this project. Thank you so much for coming, Jennifer. And next week, we're kind of straying a bit from the bi-weekly format, and next week we will be having another NavHub session with an interactive discussion afterwards, and Jake Rice will be our speaker for next week. So please attend that one as well, and you can find any of our recorded presentations on the NavHub website or the YouTube channel. So with that, welcome everyone, and thank you, Jennifer, and I'll leave it to you.
Awesome. Thank you. Thank you very much for the introduction. Good morning. Thank you. I appreciate the invitation to come speak at NavHub. I've not been able to make many of the presentations when they are live, but I've certainly enjoyed watching the talks after the fact on YouTube. It's been great to keep up with all the important work happening related to climate vulnerability. Before I start, a little bit about me. Currently, I'm a PhD candidate in the Department of Geography at Florida State University. And today I'm going to talk about part of my dissertation work, which overall focuses on improving model forecasting capabilities to better understand potential environmental changes that might impact the structure, function, and ecosystem service provisioning of coastal and marine ecosystems. And the paper that I'm going to present today stems from a collaboration that originally started while I was actually a contracted researcher working with the U.S. National Oceanic and Atmospheric Administration that I sort of continued to work on with my collaborators as a PhD student. And if you're interested in reading more about our work or viewing any of the modeled outputs from this work, I'll be including some QR codes at the end of the talk to the paper as well as to an interactive R-Shiny where you can look at some of our outputs. Okay. So the motivation of this project is very similar to a lot of others previously presented through NavHub. Ocean warming is slated to cause significant range shifts as marine species adjust their geographic distributions into higher latitudes and to deeper waters so that they can track their thermally suitable habitats. Species range shifts could have important implications both for marine ecosystems as species redistribute and also for the many fisheries and coastal communities depending on the supply of marine resources. And we're already starting to see some of these changes play out in the form of declining or shifting fish stocks, especially in places of the world like the Northwest Atlantic of the US, which is warming generally faster than 99% of the global ocean over the recent decades. So there's been a lot of really important work focused on projecting marine range shifts across multiple taxa with the aim of understanding the sensitivity of different species to warming temperatures, and often with the long-term goal of informing broader climate vulnerability assessments focused on reducing harm both to ecosystems and to people. Now, out of necessity, many earlier studies have focused on projecting changes specifically in thermal habitat, which makes sense, essentially using habitat suitability models to develop statistical relationships between historical species occurrences and ocean temperature conditions, and then forecasting out potential changes in species ranges over different spatial and temporal scales using available ocean climate projections. And generally, these thermal habitat models have been really useful for providing insights into the potential trajectories of species habitats and population changes. However, we know that species ranges can be determined by many more ecological and oceanographic drivers, including primary productivity, salinity, dissolved oxygen, acidity, and other factors, which may also themselves be affected by climate change. So at the time that we were developing this study, it was unclear how accounting for these important factors might impact range shift projections for many species, mainly because of the limited availability of climate forecasts for these other important environmental drivers. So to that end, we aimed to investigate how a focus on ocean temperature could affect assessments of marine species range shifts. And we hypothesized that species will generally be more restricted in their ability to respond to climate change than temperature models would suggest. And to test this hypothesis, we developed a sort of comparative habitat modeling study focused specifically on the Northwest Atlantic shelf, which happens to be a great place for exploring hypotheses related to climate change because we have a rich long-term monitoring data sets collected by the National Marine Fisheries Service, including a fisheries independent bottom trawl survey that operates spring and fall and uses a random stratified design to characterize trends in abundance, as well as long-term trends in species distributions. At the same time, NMFS also operates a fisheries observer program where they monitor catch year-round from a range of different gear types, including bottom trawls. From these combined bottom trawl data sets, we were able to characterize historic species distributions relative to environmental conditions and then explore potential changes in their responses. We focus specifically on benthic species, including American lobster and others, demersal species like Atlantic cod, as well as coastal pelagic species like Atlantic herring and others. To quantify historic species environmental relationships, we paired all species records with information on the oceanographic conditions and seabed characteristics from the locations and months in which the records occurred. We acquired 5 oceanographic variables from the Hybrid Coordinate Ocean Model, or HICOM. We also acquired static data layers for 2 seabed characteristics using GEBCO and then modified using the benthic terrain modeler developed by NOAA. And then to produce hindcasts of species distributions, we also acquired monthly climatological layers for the 5 oceanographic variables. We also used a climate model forecast from the NOAA Geophysical Dynamics Lab called CM 2.6, which produces monthly and yearly projections of a range of environmental factors, including sea surface temperature and bottom temperature, which likely control species rates of growth and development, sea surface salinity and bottom salinity, which could impact species physiology and also potentially be a proxy for primary productivity patterns. And lastly, sea surface height, which we are using in this case as a proxy for larger current or mixing patterns that could also affect primary productivity at some level. To test our hypothesis, we fit 2 types of habitat suitability models. Specifically, we used binomial generalized additive models for all species with sufficient records for modeling within a period of 2002 to 2014. And we essentially fit 2 types of models. We first fit a traditional thermal habitat model, which we'll call partial model, pairing species records on monthly ocean temperatures and bottom characteristics. We then fit a second model for each species, which we call a full model, using similar temperature variables along with the addition of surface salinity, bottom salinity, and sea surface height. And then in the study, we evaluate the relative performance of the 2 types of models using different metrics. We also developed hindcast predictions for the period of model development, and then compared those predictions to future climate projections of species distributions across multiple time periods, including 2020 to 2040, 2040 to 2060, and 2060 to 2080. And then we compared model outputs between the 2 types. So first, one thing we found is that in general, partial models performed pretty adequately with high levels of AUCs and other metrics, but the full models produced significantly better AUCs, percent accuracies, deviances, and delta AICs, indicating overall better performance when representing historic distributions, as well as better predictive skill when forecasting species future ranges. And when we looked at the order of variable importance for the full models, we found the reason for this. This figure shows the average percent deviances attributed to each variable, first for all species in the upper left, and then broken down by different species groups, including demersal, benthic, invertebrates, and pelagics. And what you can see is that including salinity variables and sea surface height variables frequently contributed additional model deviance, indicating that they are improving the model's ability to explain species distributions. Now, I want to acknowledge here that we are just talking about adding the effects of salinity and sea surface height, but it's likely that including other variables like primary productivity and dissolved oxygen could result in even bigger changes in model performance, as they are often considered more biologically relevant. Now, when we compared the spatial predictions of each species, we found significant discrepancies between the partial and full models. And to give you an idea of what this looks like, here are future predictions for 5 species for the time period of 2060 to 2080, with the full model predictions at the top, in the top panes, and the partial model predictions in the bottom panes. And you can see for species like black sea bass, Atlantic cod, and American lobster, there are some pretty big differences in their range distributions and suitable areas between the 2 types of models. For other species like butterfish and sea scallops, there are more subtle changes, but certainly discrepancies. And if you wanted to interactively explore some of our model predictions between different time periods and the 2 model types, there's a QR code here for our Shiny, where you can do that. And you can also look at different predictors for each species. Excuse me. Okay. So of course, we were very interested in understanding how these changes might play out across different time periods and range metrics. So we tried to do a somewhat more quantitative analysis than just like visually looking at the individual predictions. So we calculated 6 range metrics across each time period. First, we looked at the range boundaries, including the northernmost and southernmost latitude of a species range. We also looked at range centroids, which we calculated in terms of the central gravity distribution of the suitable habitat area. We looked at the range extent, or the total available area of suitable habitat. We looked at the patchiness, defined as the density of suitable patches across the study area. And then lastly, the percent aggregation, representing sort of the spatial connectivity or fragmentation of suitable habitat patches. So putting these together, we were able to calculate differences between forecasts of individual species ranges between the 2 model types across different time periods. And I'm going to show you these results in just a second, but first I want to orient you to how to interpret the figure, because it's a little much. So if the value is close to 0, it means that the full model and the partial models predict pretty similar values for most species for a given range metric in that time period. And if the value is positive, the full model predicts a larger value. And then, of course, the opposite, if the value is negative, the partial model predicts a larger value. Okay, so looking first at species range boundaries, the northern range boundary and the range centroid for both models, we see the 2 models perform pretty similarly, with each time period sort of hovering right around 0. However, the more positive southern range boundaries suggest that full models are showing more contracted ranges than partial models for a given time period. The full models also predicted more contracted range extents that were patchier, less cohesive than the partial models would have predicted for that time step. And you'll notice that over time, these discrepancies or differences between the 2 types of models amplifies over time. In addition to looking at differences in model predictions between species within time periods, we also looked at how species ranges would change overall, so between current and future predictions. Again, I'm going to show you how to interpret the figure, so it's a little less busy. If the value is close to 0, the model is predicting minimal changes in species range metrics between now and future conditions. If the value is positive, the model predicts an increase in a particular range metric for that model type. And if the value is negative, the model predicts a decrease for that model type. So looking first at species responses in terms of their range boundaries, the northern range boundary, range centroid, and southern range boundary, we found that full and partial models show a pretty similar picture of northward range shifts. Not a lot of differences. However, when you start to look at other metrics of range change, we found that full models largely show that species ranges will be significantly more contracted, patchier, and less aggregated over time into the future than the partial models would suggest. So to recap or to summarize, some of the main points of the paper. So we found that range shift models, considering a broader set of oceanographic and climate drivers, generally do a much better job at describing and predicting changes in species ranges. We also found that including more variables revealed the potential for more extreme changes in species ranges, including larger habitat shifts, leading to more contracted ranges that were patchier and more fragmented in space than the temperature models would suggest. Our findings suggest that temperature-focused models may be inadequate for assessing climate vulnerability for many species and may, in some cases, mask their true vulnerability, especially in cases where species are potentially losing a significant amount of habitat that is not predicted by the temperature models. So a main conclusion from our paper is that wherever possible, we recommend that future work related to range shifts seek to incorporate a broader range of habitat drivers to understand their potential vulnerability to this particular climate driver. And let's see. Before I take questions, I of course want to acknowledge my collaborators who have been a wonderful part of this project. I also want to acknowledge funding and support both from my current lab and department, as well as the NOAA J.J. Howard lab, where this project originally was conceived. And on the left and right, I'm including QR codes for the paper and the R-Shiny. And with that, I'll take any questions.
Great job, Jennifer. That was really interesting. So I'll open the floor for questions, but just because I don't see any hands up right away, and I do have one.
Sure.
I guess I can get us started.